Hi, welcome back. I'm going to now give you a couple more differential equation models. But something to keep in mind is that for these examples, the sum of the quantities is not a fixed value. So in the SIR model and in the product adoption model, we were talking about percentages of the population in each of the boxes. In this case, we're not necessarily talking about percentages, we're talking about quantities that are varying over time. So let's talk about two populations that are interacting. And there's two different models that we can think about this way. You could imagine maybe we have some prey and maybe we have some predators. And we're trying to figure out how do those populations change over time. And so the way we're going to set this up is we're going to say, okay, how is the prey changing over time and how is the predators changing over time? So for the prey, let's imagine bunnies, like lots of little bunnies. Bunnies, when there are more bunnies, there's even more bunnies. So if the prey were just left alone, we would expect that we would get some constant times the current population. We would expect exponential growth. But the issue is that with the predators around, depending on how many predators and how much prey there is, that's going to reduce the amount of bunnies that are hopping around because they're being eaten by their predators. So this is going to be a negative influence on how many prey there are around. On the other hand, let's say you are a predator and there's lots of bunnies to eat. So because there's so many bunnies to eat, then depending on how much, depending on how many bunnies there are and how many you there are, then that's going to positively increase the number of your population, because your population is going to grow when there's enough bunnies around, and it's also going to depend on how many of you there are around. All right? But at the same time, we also expect that when there's too many of you around, well, there's going to be competition for the bunnies. So there's going to be some negative impact based on the other competitors that there are around. And so this set of equations is called the Lotka-Volterra equations. And this setup would allow you to predict how the populations are changing over time. So you can imagine a number of different ways in which you might use this model. Well, once you've figured out how alpha, beta, delta, and gamma, all what the right ones are for the given population, you can decide, well, what happens if there's some governmental regulation about killing cute bunnies, or what if there's some about the predators to the bunnies? What if there's some change about climate or some other impact that's going to change some of these parameters? And in those cases, some metric might be changing, and so that could be something that you might want to investigate. Another aspect to this would be, let's say you had some competitive species. So let's say you've got these cute bunnies, but you also have those cute deer. And the deer and the bunnies both want to eat all the lettuce in your garden. Well, we've already seen before a parabolic growth function. So this idea that if there's only so much lettuce to go around, then if we're writing down a differential equation for calculating how many bunnies there are going to be, we got this parabolic growth function. So alpha x plus beta, minus beta x squared. And so there's some carrying capacity to this population. Now, let's say we have two populations that are competing for the same resources, and in that case, we want to figure out how do x of t and y of t change over time. And so we'll set up two different equations, dx dt and dy dt, and they'll both be some increase based on how many people there are. So we have alpha times x, alpha 1 times x, minus beta 1 times x squared. And then they'll be, for y, it'll be similar, alpha 2 times y minus beta 2 times y squared. But then there's some cross contamination, competition, where depending on how many x's and how many y's there are at the same time, those things are going to be impacting the populations negatively. So we could say this is minus gamma 1 times xy, and this one is minus gamma 2 times xy. And so these equations then would model two populations that aren't eating each other, but instead they're competing for the same resources. All right, so let me stop there, and I'll do two more examples in the next video. See you shortly.